Hello folks, Dr. Shane here. This is just kind of a quick hit video to go along with the first kombucha lab where we did the ethanol analysis. So there are a couple of questions in the post-lab discussion that are a little strangely worded. So I thought this video, it took me actually a little bit of time to get my head around them after consulting with Dr. Richardson, who is the kombucha expert, and he explained it to me and I got it now. So the two questions are, there's a calculation involved, and then there's one that talks about ideality. Okay, so before we go too far into the math of this question, so we are assuming that kombucha is ethanol and water. Okay, so if we did a calculation of ethanol and water earlier in the semester, that would have been one of those situations where we would calculate a vapor pressure, and water and ethanol are both volatile. Water not so much, but we would do that equation where we'd add up the vapor pressures and the mole fractions of water and ethanol, and that would be the vapor pressure. Okay, now that would be assuming an ideal solution. What does that mean? Okay, an ideal solution is one where there's no interaction among the particles that are dissolved in the solution. So in this case, the only particles dissolved in the standards are ethanol and water. Now there's a lot of hydrogen bonding going on there. So that's maybe not a great assumption, but the ethanol concentration is really, really low in just an ethanol water mixture. So there's probably not a lot of interaction among the ethanol molecules with like a 0.5% or 1.5%, I think was the highest concentration. Kombucha, however, has got a lot of other stuff dissolved in there. It's not just ethanol and water. Nobody would make any money, and that wouldn't have a lot of health benefits. So there's a lot of other materials in the solution. So is it a good assumption to assume that kombucha is a close enough representation to an ideal solution like ethanol and water? That's really the concept that we're after here. So you've got a lot of organics, and you can look up on the internet if you want to. It's like what kinds of things are floating around in kombucha, what kind of molecules. It's going to be a lot of big organic molecules. There's a microorganism there that's producing ethanol, but it's also during fermentation. There's a lot of other flavorings and other things that are produced that make kombucha kombucha. So ultimately here, we're trying to say, I guess in a sense, is doing the analysis the way we did it a valid way of doing it? Okay, so I'm kind of maybe rambling here a little bit, but so there's two parts to this, and the discussion question is one that's a calculation, and then there's one that's a discussion about ideality and intermolecular forces. So I'm going to try to keep this a little simple. This is just a little video to help you with that. Okay, so in the first part, and let me just chart this out for you. So basically what we're going to do is this. You get a percent of ethanol by volume off of your quadratic equation thing. So I'm not going to do all that now. So you do that. And what that does is that assumes, again, that kombucha is nothing more than ethanol and water, which we know it's not. It's much more than that. So let's just do this. And I got to get the pen going here. And all right, let's see this. There we go. So I'm going to assume you've done all this work, and let's assume you get 1.10% ethanol, and that's a volume to volume percent. So you put whatever value it is you have there. So what I did was essentially what we're going to do. If it's 1.10% ethanol volume to volume off the graph, well, therefore it's going to be what? 98. What is it? 90% water, volume to volume. Now you could say, well, I'm done now. Woo! I just converted that to a percentage by subtracting from 100. Well, that's not exactly the right thing we want to do here. So if you assume an ideal solution, this would be true. You would simply do the subtraction. 100 minus 1.10, and hopefully I did that math right. I think I did. Well, you can double check it. So what we're going to do now is we're going to use mass. What we're going to do is take this volume percent and convert it to a mass percent. This drives home a very important point in the chemistry lab. Mass is a much better way to indirectly measure volume than actual volume, especially when it's small volumes. So what does that mean? So if you measure a really small mass and you have a good density, that's a better way of getting a volume actually than using a volumetric pipette or something, especially if it's really small amounts. So mass is a way of doing volume indirectly through density. Anyway, so what's the calculation? So if it's 1.10% ethanol volume to volume, you can write this a couple of different ways. I think the easiest way to write it is that's going to be 1.10 milliliters of ethanol for every 100 milliliters, not of water. This is of kombucha. So I'm just going to use K for kombucha. Fine. So that's what that number means that when you do your quadratic equation. Now what we can do then is we can convert this to a percentage, but a mass to mass percent. Now that's pretty easy, isn't it? I mean, you just convert milliliters of kombucha into grams of kombucha, convert milliliters of ethanol into grams of ethanol using density. So I don't think you need me to show you how to do that, but I'll just set this one up. So it's just ethanol we know is let's see. Again, look all this stuff up. It's 0.789 grams of ethanol is 1 milliliter of ethanol. Okay, that works, I think. And then the kombucha, you're given the density there, but that would be easy enough to go into the lab and get a really good density of kombucha. That would not be a hard thing to do, and to have that be a very reliable number, both accurate and precise. And we know that a milliliter of kombucha is 1.08 grams. That's just given to you. You couldn't look that up on a table or anything. Kombucha is not a standard solution. Okay, and what do we have here? Well, we're going to have grams of ethanol per gram of kombucha, and then we would just multiply this by 100. And that would give you the percent by mass. Okay, now I'm just going to outline this for you. I don't think I want to do all this for you, is once you have that, so you'll have percent of ethanol by mass, well then, what's the percent water? Mass to mass. Okay, well it's 100 minus that. So here's the general logic of this problem. So you calculate the mass percent of ethanol in kombucha by doing this unit conversion. Fine. Then you take 100 minus that to get the percent of water by mass. Then you convert that answer into a volume to volume percent by using density kind of in the reverse direction. Cool. Now you've got two numbers to compare. You've got this volume to volume percent of water, which uses density, and that assumes nothing about an ideal solution, nothing. And then you have this number up here, which does assume an ideal solution. And then the idea is to compare these two numbers. That's the point. So it's a good problem, and actually this would answer a question, is the way we measured ethanol in kombucha a valid way of doing it? So that's a nice little supplemental video, and that's good because it reviews colligative properties, intermolecular forces, ideal solutions, and it refreshes us on unit conversions using mass and volume, which is really a pretty standard thing in a lab. Okay, that's it, and hopefully that was helpful to you.